The buoyant force is the force of buoyancy, which we might associate with objects that float. In other words, this is the force that is responsible for an object that is floating. But it's really there even on an object that is not floating. So even if an object sinks, there's still a buoyant force there. It's really there due to the pressure forces of the fluid that the object is in. So when an object is in a fluid, it displaces some amount of that fluid. And it turns out that a simple concept for understanding how much buoyant force there's going to be is that it is equal to the weight of the fluid displaced. And so based on that, we can understand this formula at the top of the key concepts slide for the buoyant force, which is equal to the density of the fluid multiplied by the free fall acceleration due to gravity. In other words, 9.81 meters per second squared times volume displaced. If you look at the density part with the volume, density times volume is mass, and mass times g is weight. So this really is describing the weight of the fluid that is displaced. Now we have two more formulas here, one of which applies to submerged objects and lets you calculate the buoyant force on a submerged object, and the other one is for a floating object. Now, for these two formulas, one could say that generally we're imagining objects that are not hollow, right? Solid objects that have a well-defined density. So we're not talking about things like submarines or boats, although one could argue that maybe one could apply these formulas to those kinds of objects. But like if you said, hey, could I apply this one here to a submarine? Part of this formula is the density of the object. Well, if you said, okay, maybe the submarine is mostly made out of steel, would this be the density of steel? The answer is no. It would sort of have to be the average density of the submarine and all of its contents, including all the air spaces in the submarine, in order for this formula to work correctly. But generally speaking, these two formulas work best for solid objects that don't have like hollow air spaces in them. Those two formulas actually connect to a bigger concept, which is the idea of relative density, which is commonly referred to as specific gravity. As an example here, I've stated on the whiteboard that the specific gravity of a substance in water is equal to the ratio of the density of that substance to the density of the water. And the way this works is if the specific gravity of a substance is larger than 1, it means that a solid sample of that substance is going to sink, and one can calculate the buoyant force on that sunken object. So like if I drop, say, a piece of metal into some water, it sinks, and then I say, well, is there still a buoyant force on it? The answer is yes. I would take the weight of that metal and I would divide by the specific gravity, and that would be a buoyant force that is less than the weight of that metal, which is consistent with the idea that that's why it sinks, because the buoyant force is insufficient to keep it floating. So again, this formula kind of lends itself to those type of situations. This last formula here is for a floating object and relates the fraction of the object that is submerged to the what really represents the specific gravity. So another way you could restate this formula here, if we interpret density of the object, the ratio of density of the object to the density of the fluid as the specific gravity, as in, if it were water, it would be the density of water instead of just some whatever fluid, right? If we multiply both sides by volume of the object, and then here I kind of left off some of those subscripts, but we get the very simple statement that the volume displaced of this floating object is the specific gravity times the volume of the object. And like I said, both of these really only apply to solid objects, not to hollow objects that have air spaces like submarines and boats.